here you have the scenarios where we performed this, where we carried out this study. This is the simulation environment. This is a OpenNet simulation software. This is our model for the 15.4. On the right-hand side, you can see the experimental test bed. The two scenarios are very identical. They both have one PAN coordinator, 10 devices. These devices are going to generate traffic at given inter-arrival rates to create some network load. And we have a network analyzer here that is going to catch all these packets and make all the necessary computations to perform the performance evaluation. Obviously, although these scenarios are very identical, it's obvious that you have on the experimental scenario you have things like interference from other wireless sources. You have process limitations and memory constraints which are not accounted for on the simulation scenario. So these are the results for beacon order. This was one of the parameters we studied. So which we observed on the left hand side you have the results from the simulation model, and on the right hand side from the experimental test bed. What we observe is that the throughput decreases with lower beacon orders, which means that when you have low beacon orders like 1, 2, 3, you get really lower throughput. And this is due, we found out this is the reason for this is that with lower beacon orders, this is obvious you have much higher overhead of beacons, and due to the difference problem, which I don't have a figure here, but this means that if you don't have enough time to transmit your frame, you do your back off in the CSMSA, you do your back off, then you don't have enough time to transmit the full frame, so you're going to defer it to the next super frame. But when you're going to transmit, you're just going to do 2 CCAs and then transmit that frame. And every other device is going to do the same, which means that there will be collisions there. And this is especially visible with lower beacon orders. So the results are very similar, although there is some difference, 10% difference, 15% difference between the two scenarios, but the behavior is the same. So regarding the second contribution, the hidden node avoidance mechanism. Hidden node problem happens, you probably know this, happens when two nodes that are not visible to each other transmit at the same time, and that results in a collision on a third node. This is a major source of quality of service degradation, especially in wireless sensor networks, due to the limited communication range of sensor nodes, the radio links asymmetries, and obviously the physical environment itself. And this has impact in metrics like throughput, on energy efficiency, and on message delay. We analyzed several proposals to solve this or to mitigate this problem. We got to the conclusion that, in fact, none of those was really adequate for this special case, to the particular case of wireless sensor networks, due to the fact that you have to work with limitations in terms of energy efficiency and communication bitrate. So we proposed HNAME, which is a proactive mechanism to solve this problem. What HNAME does is that it groups visible nodes and assigns to those nodes, to those groups, a portion of the cap where these nodes will be able to contend for the median. For instance, on cluster T, these nodes are visible to each other, however they cannot see these ones nor this one. So the idea is to group these nodes here, to assign a portion of the cap, which they are assigned in a portion of which we call gap, which stands for group access period. So we assign this group to them. To these nodes, they could be fit, for instance, on group 2, and to this one, he could be fit on group 3, or he could just transmitting the gap. This means that these nodes will be able to transmit content from the medium without any collision due to the hidden node problem. It's a kind of a TDMA, but with CSMA contention. So this is the algorithm we use for doing this grouping. I will not go into details, but I can explain later on if you are interested. So we tested this. We experimentally we built a test bed where we placed it had 18 MicroZ nodes. So we had a group of 6 nodes here, another 6 nodes there, and some other there. These were not visible to each other, so they were hidden. These are some obstacles. These are walls, and you had then we had a ZigBee coordinator that was and a sniffer to get all the traffic. So the testbed is similar to the one I presented before for the CSMACA performance evaluation. Again, the modes were programmed to transmit traffic at given interval times. We analyzed the throughput and the probability of success, and we came up with those results. Here you can see the throughput result for, this is a probability of success, by the way. So you can see the throughput result for this testbed without HNAME. I mean, where all nodes are transmitting and with hidden nodes problem. Okay. The red line is the same testbed with HNAME, which you can see it's a tremendous difference in performance, over 100%. So another curious thing is that without hidden nodes, I mean, just picking up all these nodes, putting them in a way they are visible to each other, you get this green line throughput, which is actually slower than using HNAME. And this is easily explained by the fact you don't have so many nodes competing for the medium at the same time. Again, we wanted to test this in a real-world scenario. I mean, to actually see, to have the feeling of how much the hidden node problem would affect a real-world application. To do this, we used a testbed that was previously developed. It was a search and rescue testbed. The idea was to capture or to find the target. So you have 2 mobile robots. One target robot was remote controlled and was remote controlled in a sensor network. The sensor network was there to localize and to track that target robot, and then you would have a rescue robot that would go towards that target. So we changed this testbed to have some, and we placed some hidden nodes where we call the hidden node zone. These results are for a second test. We just placed, in fact, one hidden node. So in this area, these are anchor nodes used for localization of the targets. We placed one hidden node here, and we programmed it